Hello friends, welcome to this YouTube channel. Today we are going to solve 3 numerical problems on 3-phase induction motors. By solving these problems, we shall learn how to compute equivalent circuit parameters of a 3-phase induction motor from its Blocked-rotor test results. We shall also learn how to calculate starting torque of this motor. The Blocked-rotor test of an induction motor is similar to the short circuit test of a transformer. That is why the Blocked-rotor test is also known as short circuit test. When Blocked-rotor test is performed, the rotor is kept locked by some means so that it cannot rotate. Therefore, slip S equals to 1. A 3-phase auto transformer is used to provide 3-phase AC supply to the stator at rated frequency. Voltage is gradually increased from 0 to a value so that rated current flows through the stator winding. Since slip S equals to 1 with a much lower voltage than rated voltage, rated current flows through the stator winding. Due to smaller voltage, produced flux will be less. Therefore, core losses under Blocked-rotor condition may be neglected. Under Blocked-rotor condition, for a star-connected 3-phase induction motor, blocked rotor voltage per phase VBR equals to VL by root 3, where VL is the line-to-line stator voltage measured by the voltmeter. Blocked-rotor current per phase IBR is measured by the ammeter. Taking summation of 2 wattmeter readings, we get input power PBR equals to W1 plus W2. Since under Blocked-rotor condition, rated current flows through the stator and rotor windings, PBR is the measure of full load copper losses. That is, PBR equals to IBR square into Req, where Req equals to R1 plus R2 dash. Now we shall observe how to compute equivalent circuit parameters from the Blocked-rotor test results. Let us first draw the equivalent circuit per phase for a 3-phase induction motor. Since at reduced voltage both Im and Iw are negligibly small, parallel branches may be open circuited. Now we shall redraw the equivalent circuit. Per phase equivalent impedance referred to stator ZEQ equals to VBR divided by IBR. Per phase equivalent resistance referred to stator Req equals to PBR divided by 3 times IBR square, that is equal to R1 plus R2 dash, where R1 is the stator resistance per phase and R2 dash is the rotor resistance per phase referred to stator side. Stator DC resistance per phase may be measured using a multimeter. The measured value should be multiplied by a factor of 1.2 to get AC value of stator resistance per phase, that is R1. By subtracting R1 from Req, we get R2 dash. Per phase equivalent leakage reactance referred to stator XEQ equals to root over ZEQ square minus Req square, that is equal to X1 plus X2S dash, where X1 is the stator leakage reactance per phase and X2S dash is the rotor leakage reactance per phase at standstill condition referred to stator. By no means X1 and X2S dash can be separated. Therefore, it is convenient to take x1 equals to x2s dash equals to xq by 2. A three-phase star-connected induction motor is tested in the blocked-rotor test. Its rated line current of 8.5 ampere is drawn when the line voltage is 16.6 volts and the total input power is 48.8 watts. Under these conditions, we have to determine the equivalent resistance referred to the stator per phase, the equivalent impedance per phase, and the equivalent leakage reactance per phase. Let us first write down the given block-rotor test data. Since the stator is star-connected, block-rotor voltage per phase VBR equals to 16.6 divided by root 3, that gives us 9.584 volts. Block rotor current per phase IBR equals to 8.5 ampere. Input power PBR equals to 48.8 watts. Let us now draw the equivalent circuit under block rotor condition. Per phase equivalent resistance referred to stator Req equals to PBR divided by 3 times IBR square. Using values we get 48.8 divided by 3 into 8.5 square, that gives us 0.225 ohm. Per phase equivalent impedance referred to stator ZQ equals to VBR divided by IBR. Using values we get 9.584 divided by 8.5, that gives us 1.1275 ohm. Per phase equivalent leakage reactance referred to stator XEQ equals to root over ZEQ square minus REQ square. Using values we get root over 1.1275 square minus 0.225 square, that gives us 1.1048 ohm. A 10 kilowatts 420 volts 3-phase 4-pole 50 Hz delta connected squirrel cage induction motor gave the following data for blocked rotor test: 210 volts, 20 ampere, 5 kilowatts. Stator core loss at rated voltage and frequency is 300 watts. The DC resistance measured between any two stator terminals is 0.6 ohm. We have to determine the starting torque at rated voltage and frequency. Let us first write down the given data. Supply voltage per phase V1 equals to 420 volts. DC resistance measured between any two stator terminals RDC equals to 0.6 ohm. Let stator DC resistance per phase be R1 DC. Expression for DC resistance between any two stator terminals RDC equals to R1 DC parallel with R1 DC plus R1 DC, that is equal to 2/3 R1 DC. Therefore, expression for stator DC resistance per phase R1 DC equals to 3/2 RDC, that is equal to 3/2 into 0.6, that gives us 0.9 ohm. Multiplying this value by 1.2, we shall get AC value of stator resistance per phase R1 equals to 1.2 times R1 DC, that is equal to 1.2 into 0.9, that gives us 1.08 ohm. Given Blocked-rotor test data, blocked-rotor voltage per phase VBR equals to 210 volts. Since the stator is delta connected, blocked-rotor current per phase IBR1 equals to 20 upon root 3, that is equal to 11.547 ampere, and input power PBR1 equals to 5 kilowatts, that is equal to 5000 watts. At rated voltage, blocked-rotor current per phase IBR equals to IBR1 into V1 by VBR. Using values we get 11.547 into 420 by 210, that gives us 23.094 ampere, that is the stator current per phase at standstill condition when rated voltage is applied. Blocked-rotor input power at rated voltage PBR equals to PBR1 into V1 by VBR whole square. Using values we get 5000 into 420 by 210 whole square, that gives us 20,000 watts. That is the stator input power at standstill condition. Given number of poles of the motor P equals to 4. Supply frequency F equals to 50 Hz. Let us now determine synchronous speed. Ns equals to 120 F by P. Using values we get 120 into 50 divided by 4. That gives us 1500 revolutions per minute. Now we shall determine rotor input power at standstill condition. Pg equals to Pin minus Ps minus 3 times I1 square into R1. Given stator core loss Ps equals to 300 watts. We have obtained stator input power at standstill condition Pin equals to 20,000 watts. Stator current per phase at standstill condition I1 equals to 23.094 ampere, and stator resistance per phase R1 equals to 1.08 ohm. Using values we get Pg equals to 20,000 minus 300 minus 3 into 23.094 square into 1.08, that gives us 17,972 watts. Expression for starting torque developed. TST equals to Pg divided by 2 pi Ns by 60. Using values we get 17,972 divided by 2 pi into 1500 by 60. That gives us 114.4133 Newton meters. Blocked-rotor test on a 3-phase 40 kilowatts 400 volts 50 Hz 6-pole star-connected induction motor gave the following data: 200 volts, 110 ampere, 0.4 power factor. Neglecting magnetizing current and assuming stator and rotor ohmic losses equal, we have to compute the starting torque for a 3-phase voltage of 320 volts at 40 Hz. Let us first write down the given blocked-rotor test data. Since the stator is star connected, blocked-rotor voltage per phase VBR equals to 200 by root 3 volts. Blocked-rotor current per phase IBR equals to 110 ampere and power factor cos phi BR equals to 0.4. Let us now draw the equivalent circuit under block-rotor condition. Per phase equivalent impedance referred to stator ZQ equals to VBR divided by IBR. Using values we get 200 by root 3 divided by 110, that gives us 1.0497 ohm. Per phase equivalent resistance referred to stator Req equals to ZQ into cos phi BR. Using values we get 1.0497 into 0.4, that gives us 0.42 ohm, that is equal to R1 plus R2 dash, where R1 is the stator resistance per phase and R2 dash is the rotor resistance per phase referred to stator side. Since the stator and rotor ohmic losses are equal, stator resistance per phase R1 equals to R2 dash equals to 0.42 divided by 2, that gives us 0.21 ohm. Let us now determine per phase equivalent leakage reactance referred to stator. XEQ equals to root over ZEQ square minus REQ square. Using values we get root over 1.0497 square minus 0.42 square, that gives us 0.962 ohm. Case 1. Supply frequency F1 equals to 50 Hz. We have determined per phase equivalent leakage reactance referred to stator XEQ equals to 0.962 ohm. Case 2. Since the stator is star connected, supply voltage per phase V2 equals to 320 by root 3 volts and supply frequency F2 equals to 40 Hz. Since equivalent leakage reactance is proportional to supply frequency, in this case, per phase equivalent leakage reactance referred to stator XEQ2 equals to F2 by F1 into XEQ. Using values we get 40 by 50 into 0.962, that gives us 0.77 ohm. We have obtained per phase equivalent resistance referred to stator Req equals to 0.42 ohm. Expression for per phase equivalent impedance referred to stator ZEQ2 equals to Req plus JXEQ2, that is equal to 0.42 plus J 0.77 ohm. This may be written in polar form as 0.877 ohm at an angle 61.3856 degree. Let us now calculate starting current. IST2 equals to V2 divided by ZEQ2. Using values we get 320 by root 3 divided by 0.877. That gives us 210.66 ampere. Given number of poles of the motor P equals to 6. During case 2, supply frequency F2 equals to 40 Hz. Let us now determine synchronous speed. Ns equals to 120 F2 divided by P. Using values we get 120 into 40 divided by 6. That gives us 800 revolutions per minute. We have determined Starting current IST2 equals to 210.66 ampere and rotor resistance per phase referred to stator R2 dash equals to 0.21 ohm. Expression for starting torque developed TST equals to 3 times IST2 square into R2 dash divided by 2 pi ns by 60. Using values we get 3 into 210.66 square into 0.21 divided by 2 pi into 800 by 60. That gives us 333.7 Newton meter. So today we have solved 3 numerical problems on 3-phase induction motors. By solving these problems, we have learned how to determine equivalent circuit parameters of a 3-phase induction motor when its blocked-rotor test results are available. We have also learned how to calculate its starting torque. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.